to fundamental issues as to what is happening. And we are very eloquent faculty, and chief is Professor Manoj Gupta. So we are indeed very happy that IIMS Rishikesh is the right forum, which is, and we are on what you call as a hub and spoke model. We are very keen that education must be spread everywhere. And that is the reason all our lectures are also on the website. Anyone from anywhere in the world can see and read what the faculty is teaching. This is a special moment when a phenomenal number of 4-figure registration is there. And this is all salute to Professor Manoj Gupta, who is well known for his, I would say, expertise on this subject. So I would say best wishes and thank you. And hopefully we would go into more and more into micromanagement system on individualized case basis as to what should be done in a case compared instead of a, I would say, blunder or bust. One treatment for all. We should be able to tailor the treatment more based on this radiobiology. So thank you very much. And I'm sure this information will be immensely useful for the patient welfare, for the knowledge of the student, and for the knowledge of faculty as well. Thank you.
Thank you very much, sir. Over to Deepa. Deepa, I think Dr. Vijay Anand Reddy is also here.
Yes, sir.
Prashant, may I request you to please?
Hi, Manoj. And, yeah, thank you very much. And I'm really sorry to join you late. I was in a board of meeting, directors meeting. I'm sorry. Anyway, congratulations to Dr. Manoj. Anything you say is less, dear friend. You're the master batsman in the field of radiobiology. And actually, I was telling to my students, Dr. Manoj, with the limited facilities, limited infrastructure, he did not lose his dedication or focus, and he has done wonders. And he has proven that with whatever facilities that you have, you can show wonders to the world. So that kind of a man that he is, and he's proved himself to be the best in our radiation oncology community. So looking at the numbers of registrations that what we see today, unbelievable. Unbelievable. So people called me as a Sachin Tendulkar, but I would call him as a master batsman in the field of radiobiology. God bless you, Dr. Manoj. All the very best, and I'm sure the students would really look at, listen to his longest innings of ever-ending batsman, that you can concentrate and still focus for long hours and continuously talk about a single subject without any tiredness. Hats off to you, Manoj. All the very best and good luck to the students.
Thank you, Dr. Vijay. Thank you very much.
Thank you, sir. We will start the academic sessions. So for this, I invite the course director, Professor Manoj Gupta sir, who is only faculty for this session. And I'm not giving a formal introduction from all faculty, all the office bearers we have heard. He's such a wonderful teacher, and all of you will know it from the sessions which you are going to attend. Over to you, sir, Manoj.
Thank you, Dr. Deepa. So I'm just sharing my screen. Can you see my slides, Dr. Deepa?
Yes, sir. You can put it in slideshow.
Okay, so all right. So can you see now in
yes,
slide
sir.
mode? Okay. And audible clearly, Dr.
Yes,
Deepa?
sir. Yes,
okay.
Sir. You're audible.
So thank you very much once again. And before I start, I would like to suggest all the participants that you need to focus on the screen, and you know, the concepts of radiobiology are interlinked, which means that if you are not able to understand one concept, then it will not be possible for you to understand the subsequent part of it. So I would like to all of you to focus on the screen. I have used many, you know, animations and special effects to make the subject simple. And I will start from the very basics. In my first module, I will discuss many concepts belong to many areas. For example, interaction of radiation with matter, the cell cycle, the checkpoints, the mechanism of action. So, but I will not discuss in detail of all these aspects, because I presume that all of you already aware about these concepts. The purpose of again, giving the passing reference about these concepts is that just to refresh your knowledge, because to understand radiobiology in a better way, you need to have the knowledge of all these concepts. So let me start from the very basics. That is my first slide, and I will start from what is radiation. Now, radiation is basically energy emitted from an atom or nucleus in the form of waves or particles, and there are two types of radiation. One is called ionizing radiation, the other is called non-ionizing radiation. Now, ionizing radiations are radiation which causes ionization of the atom through which they passes. And what I mean by ionization, the ionization meaning is that when these radiation passes through any atom, they eject one electron from that atom. As a result, you have a pair ion production. The ejected negatively charged electron and rest of the atom which is positively charged. And the examples are X-rays, beta rays, gamma radiation, and alpha particles. The non-ionizing radiations are radiations which are not able to cause ionization in the atom through which they passes. So they don't have enough energy to cause one electron to be ejected out of the atom. So they are not able to ionize the atom. And the examples are radio waves, sunlight, your tube lights. These are all non-ionizing radiation. As I said, that as a result of ionizing radiation, you have a pair production of ion, that is negatively charged electron plus the positively charged rest of the atom. Now, there are two types of ionizing radiation. One is electromagnetic radiation, the other is particulate radiation. The electromagnetic radiations are basically in the form of waves. They travel with the speed of light. They have two components, that is electrical and magnetic component, which propagate perpendicular to each other. And the examples are X-rays and gamma radiation. Particulate radiations are radiation which consist of particles which have got some mass. For example, electron, proton, neutron. So these particles radiation may be charged particle or may be uncharged particle. And remember that ionizing radiations are important biologically, because ionization is the property which brings death to the cells. Non-ionizing radiation cannot be used for treatment of malignant disease. Now, this is the spectrum of electromagnetic radiation based on their energy, but as a radiation oncologist, we are mainly consider the high energy electromagnetic radiation. Now, they have different penetrating power. For example, alpha has the least penetrating power and it can be stopped by a thin paper, which means that alpha particle cannot penetrate skin. Then beta particles have slightly higher penetrating power than alpha. It can be stopped by layer of clothing and they can, penetrate skin, but they cannot go deep inside the body. Then we have X radiation or gamma radiation. These are highly penetrating radiation. They are stopped by several feet of solid material and they can penetrate deep inside the body. So depending upon the penetrating power, they are categorized. Now with this background, if I say what is the definition of radiotherapy, I usually ask this question when in my physical classes, and the common mistake which students used to do, they will simply say that treatment of disease by radiation. Now, that is not the complete definition, because as I have shown to you that non-ionizing radiation cannot be used for treatment purpose. So unless you use the word ionizing, your definition is not complete. So we can say that radiotherapy can be defined as treatment of the disease by ionizing radiation. Now, there is no difference in properties of X radiation or gamma radiation. Remember, the only difference lies in their production, and we know how X-rays are produced and how gamma radiations are produced. X-rays are produced, just to remind you, X-rays are produced when fast-moving electrons are made to stop by some heavy metals like tungstens. X-rays are produced. And gamma radiations are produced from the nuclei of certain atoms. Now, these atoms are highly unstable, and in order to get stability, the atom or nucleus of these atoms disintegrate continuously and emitting certain types of radiation. And one of the radiation is gamma radiation. The other types of radiations are beta and alpha radiation. Now, this phenomena is known as radioactivity, and these atoms are called radioactive atoms. So, as I said, that only difference lies in production, no difference in the property. So whenever I will talk about X-ray, it is equally applicable to gamma radiation and vice versa. Now, depending upon energy, they have been classified or they have been given different names. For example, up to 20 kV X-ray, we call Grange rays. From 20 to 120 kV, diagnostic X-rays. 120 to 300, ortho voltage, 200 to 1 MeV, intermediate X-rays, and 1 MeV upward mega voltage X-rays. And as a radiation oncologist, we are only interested in mega voltage X-rays. Now, what happens when radiation passes through some matter? Now, it has been observed that the intensity of exit beam, when radiation passes through some matter, the intensity of exit beam is always less than intensity of incidence beam. So what happens basically when these radiation passes through matter? If you put a detector in front of this matter, what will happen? I have taken 3 photons. So what happens that one of the photon will just change its direction and it will not fall on the detector, which means that this photon will not be measured. This is called scattering. One photon will pass and will be absorbed by this matter itself. And this is called absorption. Out of 3, only 1 photon will pass unchanged and will fall on the detector. So you can see that out of 3 photons, only 1 photon passed unchanged and fall on the detector. And that is the reason that intensity of exit beam is always going to be less than intensity of incidence beam. And these two processes of absorption and scattering is known as attenuation. And we know that attenuation depends upon so many factors. For example, it is directly proportional to thickness of material. More the thickness, more is the attenuation. It is directly proportional to atomic number of the material through which it passes. More the atomic number, more is the attenuation. It is directly proportional to density of the material and inversely proportional to the energy of the photon, which means lesser the energy, more is the attenuation and vice versa. Now remember that attenuation is an exponential function of the thickness of the matter. And here we need to understand what we mean by exponential function. Now this is very important because this will come again later on in reference to cell survival curve. So I would like all the participants to focus on the screen and try to understand what we mean by exponential relationship. Suppose you have a radiation beam of 100 rad. And in the path of beam, if you put 1 centimeter thickness rod of some matter, and suppose it absorb or it attenuate 10% of the radiation beam. Now, again, in the path of beam, you put the same material, same thickness rod, it will again attenuate 10%. Similarly, again, you put another 1 centimeter thickness of the same material rod, again, it will absorb 10%. So you keep doing this with the same thickness, with the same material. Every time you put one rod, it will absorb 10%. So what are you observing here? That similar increment in the thickness of the material result into similar attenuation or similar percentage absorption of the radiation. Every time it will absorb 10%. But if you look at the absolute number, what is happening in absolute number? Now look at here. Initially, the first rod will absorb 10 rad. Second rod will absorb 10% of 90 rad, that is 9 rad. Third rod will absorb 10% of this 81 rad. So in absolute terms, it is different quantity, but in percentage wise, it is same. When this kind of relationship we see, we call it an exponential relationship, which means that addition of the same thickness of the material will reduce the intensity by same fraction or same percentage, but not by same number. And this relationship is called exponential relationship. I hope all of the participants could understand now. And if you just draw this relationship on graph, how does it look like? Now on a normal graph, it is something like this. It is called hyperbola curve. On a semi-logarithmic graph, what is semi-logarithmic graph? I will discuss in subsequent module. On a semi-logarithmic graph, it will be a straight line. Now, if you just concentrate on left panel on a normal graph, you will observe that as the thickness of the material increases, the intensity decreases, but here this curve becomes parallel to this horizontal axis, which means that this curve will never touch your horizontal axis. It means that intensity of radiation can never become zero. So what does it tell us? It tells us that whatever thickness of the material you put in the path of radiation beam, you can never make the intensity zero. And that has an application in our day-to-day practice. Many of you who are working on cobalt machine must be using shielding block. If I ask you what is the thickness of shielding block, usually shielding blocks are made of 5 HVL value. In case of cobalt, when you are using lead shielding block, it comes out around 5 or 5.5 centimeter. And this will reduce the intensity to around 3%. So if somebody asks you, if we use 10 centimeter thickness of the block, it will reduce to 0. The answer is no. And in examination, it is usually asked why you cannot make it 0, because the answer is simply because it has got an exponential relationship with thickness of the tissue. And whenever two parameters have exponential relationship, then by increasing one parameter, the other parameter can never, you can never get a 0 value. So I hope now you understand the exponential relationship. So now coming on back to what happened to the absorbed radiation. So when radiation, interact with some matter, either of the three processes may take place. What? Number one, either it will just deflect it from its path without any true absorption as reflected by the same thickness of the arrow. And then this process is called scattering, or there may be deflection as well as true absorption as reflected by the less thickness of this arrow. Now this is called scattering and absorption, or it can disappear completely, and this is called true absorption. Now coming on to the atomic structure, we know that atomic structure, in any atom consists of a nucleus which contains a positively charged proton and uncharged neutron. Around the nucleus, we have shells. In these shells, the negatively charged electron revolves around the nucleus. Now, there are many shells, and these shells are labeled as K, L, M, and etc. Important point here is that these electrons are, bound with the nucleus with a force which is called electrostatic force, and this is also called binding energy. Another important point here is that closer the electron with the nucleus, higher is the binding energy. Away from the nucleus, less is the binding energy. So based on this electrostatic force or the binding energy, the electron has been categorized into two categories in any atom. One is known as bound electron which are very near to the nucleus, and they are strongly bound with the nucleus with the electrostatic force. Electron which is farthest from the nucleus is known as free electron because the binding energy is very weak. Binding energy is very less. So these are called free electron. Now this is just to give you an example of lithium atom. Here you can see nucleus consists of 3 proton and 4 neutron, and electrons revolve around the shell. All right. Now you must also understand the difference between excitation versus ionization. Now in excitation, what happens that one of the electron in any shell gain some energy so that it moves further away from the nucleus into an outer shell, but it remains inside the atom only, and then we call it excitation. In ionization, what happens that an electron is completely ejected out of the atom. As a result, you have ion pair production. The negatively charged electron and positively charged rest of the atom. So that is the difference between excitation and ionization. Same thing here again, you see it gains some energy so that it moves further away from the nucleus. This is called excitation. In ionization, it gains enough energy so that it is completely ejected out of the atom. And then we have a negatively charged electron and positively charged rest of the atom. Now coming to the interaction of radiation with matter, as I said that I will not go into detail. I presume that all of you know about all these interactions. Now total process are 12, but important are these three: photoelectric, Compton, and pair production. Scattering I have included just to show you what I mean by scattering. Once again, that there is no true absorption. This photon will just change its direction. You can see there is no true absorption. So this is called scattering. Now coming on to photoelectric effect. Now here it occurs with the bound electron, and now we know what we mean by bound electron. Now here the photon will disappear completely and it will eject this innermost electron. Now what happens to the energy of this incidence photon? Now some of the energy is utilized to overcome the binding energy, and rest of the energy is given to this electron in the form of kinetic energy. For example, if the incidence photon has an energy of 100 keV, and suppose binding energy is 40 keV, then 40 keV will be utilized to overcome the binding energy, and remaining 60 keV will be given to this electron in the form of kinetic energy. Again, just to have an idea more clear, now you see this photon interact with innermost electron, completely disappeared and ejected the innermost electron. So this is basically the photoelectric effect. Now what happens? Now this innermost electron, when it is ejected, a vacancy is created here and atom gets unstable. So in order to get stability, the electron which is in next shell will fall down and fill up this vacancy. Now since there is a change in the location or the position of this electron, there is a change in energy. So this excess energy is emitted in the form of characteristic radiation. So what happens that when this electron is ejected, vacancy is created, this electron will fall here, characteristic radiation will be emitted. Now this vacancy is created, so this electron will fall here, and again the characteristic radiation will be emitted. Now this vacancy is created, this electron will fall here. So the process will continue till the atom gets stability. So again, with this animated video, you can see that this innermost electron has been ejected, the vacancy is created. Now from outer shell, the electron fall down and fill the vacancy, and this characteristic radiation is emitted. So if you look at the byproduct of the photoelectric effect, there are mainly the photoelectrons. These are the electrons which have been ejected out and they interact with other atoms. The characteristic photons usually of low energy, so they absorb in the matter. Important point here is that photoelectric absorption is directly proportional to the atomic number, which means that higher the atomic number, more will be the photoelectric absorption. It is indirectly proportional to the energy of the photon, which means less the energy, more will be the photoelectric absorption. Now these feature result into differential absorption in body. So what we mean by differential absorption? We know that different tissue in the body have different atomic number. For example, bones have highest atomic number, so they will absorb maximum radiation by photoelectric absorption. And that is why they appear white on an X-ray film. Soft tissue absorb less than bone because they have less atomic number than bone. So these structures will appear gray on the X-ray film. while air containing structures such as lungs, they absorb least radiation, so they appear black on the film. And this is basically what I mean by differential absorption. And differential absorption is needed in which branch of medicine? In diagnostic radiology. So the question is that what energy of X-ray we should use so that we can have differential absorption in the body. Again, answer is, as I said, that photoelectric absorption is indirectly proportional to energy. So less the energy, more will be the photoelectric absorption. So we should use low energy X-ray in diagnostic radiology. That is, energy in the range of kilo electron voltage should be used, which will cause photoelectric absorption and ultimately which will result into differential absorption inside the body. Now the next question is, can we use it in radiation oncology? Answer is no. Why? Because there is a differential absorption. Suppose you have a tumor inside the pelvis. So if you treat with low energy X-ray, because of photoelectric effect, the bones will absorb maximum radiation and very little radiation will be delivered to the tumor. So there is a shielding effect by bone. So that is why low energy X-ray cannot be used for therapy purpose. So to summarize the photoelectric effect, there is an interaction with bound electron. Incident photon disappear completely. There is a differential absorption depending upon the atomic number of the tissue, predominantly seen in diagnostic radiology. It is not suitable for radiotherapy as shielding effect of the bone will be there. Now coming on to Compton effects. So in Compton effect, what happened, it is just the opposite of photoelectric effect. Now it occurs with the free electron. And there is a billiard ball like collision. I'm pretty sure that all of you must have seen billiard game where you can see, you can observe how one ball collides with the other ball. I will just show you some videos regarding this. So it is a billiard ball like collision. No energy is lost in dislodging the free electron because, as I said, that binding energy is almost negligible. So this photon will not lose any energy in dislodging this electron. Whatever energy this photon will lose, this is because some of the energy will be given to this electron in the form of kinetic energy. So that is the energy which this photon will lose. This photon will be deflected in a different direction with slightly less energy, and this will again interact with the electron of another atom, and this process will continue till this photon loses all its energy. So in Compton effect, you can see that the photon will interact with the outermost electron. It will eject it and it will deflect it in a different direction with slightly less energy. Now, there are two extremes of collision of this photon with electron. Now, one is known as sliding collision, the other is known as head-on collision. Now, in sliding collision, what happens that the photon will hit at the edge of electron. And when it hits at the edge of electron, it will give very little energy to this electron in the form of kinetic energy. And the photon will be deflected in forward direction with slightly less energy. So just look at here. What happens that it will hit at the edge, very little energy to this, and it is deflected in a forward direction, and then it will interact with another electron of another atom. Now, if you look initially the direction of the photon, it is something like this. Had there not been any collision, it would have gone like this. But because of collision, the photon is deflected in a new direction. So this is called angle of deflection. And remember, minimum angle of deflection, minimum energy is given to this electron in the form of kinetic energy. Head-on collision, what happens? That this head-on collision of the photon with the electron, and all the energy is given to this electron in the form of kinetic energy, so that this electron will move in forward direction with a very high speed, and this photon will collide and bounce back. So look at this screen, what happens, that it will head-on collide, give all its energy, it moves with very fast speed and it bounces back. So what happens that if this is the initial direction of collision, initial direction of the photon, had there not been any collision, it would have gone like this, but there had been a collision and this had bounced back. So this forms the angle of deflection. So here we observe that maximum angle of deflection result maximum energy given to this electron in the form of kinetic energy. And remember that most of the collision occur between these two extremes, either minimum angle of deflection or maximum angle of deflection. Minimum kinetic energy given to this electron or maximum kinetic energy given to this electron. So this is just to show you how a ball collides with other. Now this is just depicting an example of head-on collision. Consider this as a photon, this as an electron, and what you will observe that there will be head-on collision and this ball will move very fast in the forward direction and this collides back. So this is exactly what happens, in interaction of radiation with matter. Then this is a sliding collision. Again, you consider this as a photon and this as an electron, and you will just observe that this ball will hit at the edge and very little energy. So with very little speed, this ball will move forward and this photon or this ball will be deflected in a new direction with very, with a high speed. So you can see this ball is deflected in the forward direction. I hope you understand now. So Compton effect is directly proportional to energy. More the energy, more will be the Compton effect. It does not depend upon the atomic number, which means that there will not be any differential absorption in Compton scattering. Of course, it directly proportional to electron density, but most of the body tissue have the same electron density. So there will again not be any differential absorption. So we can say that there is no more dose absorption in bone or shielding effect as seen in photoelectric absorption. So we can say that Compton scattering is an ideal way of interaction in radiation oncology. So just to summarize, it occurs with free electron. There is no differential absorption in the body. It increases with increasing energy. It is a predominant process in radiotherapy. Now, third is pair production. Now, what happens in pair production? Now, it only occurs when the incidence photon has an energy of more than 1.02 MeV. If energy is less than this, then this interaction will not occur. Now, when photon has such a high energy, it does not interact with electron. It will go directly into the nuclear field and convert this photon into two particles of opposite charge, that is electron and positron. Now, any energy which is in excess of 1.02 MeV will be shared by these two particles in the form of kinetic energy, and then with this energy, these particles will move in the medium. And when they move in the medium, they will further causing ionization of the atom of that medium, and they lose their energy and they come to rest. And when they come to rest, they annihilate each other to form two photons of 0.511 MeV each. So that is called annihilation reaction. So this is the whole process of pair production. I'm pretty sure that your physicist must be teaching you in detail about all these interactions. So just with this animated video, you can see that this photon will go into the nuclear field, will convert into two particles of opposite charge, that is positron and electron. Now, important point here is that this process is directly proportional to the atomic number, which means that higher the atomic number, more will be the absorption. So this process again result into differential absorption. This process is also directly proportional to the energy of the incidence photon, which means higher the energy, more will be the pair production. In fact, pair production is predominantly seen at energy more than 20 MeV. In fact, the relative contribution of pair production in less than 20 MeV is very, very small. Now, have you ever wondered why the commercially available linear accelerator are manufactured only at less than 20 MeV X-rays? The reason is this: because if you manufacture linear accelerator with more than 20 MeV X-ray, then pair production will be the predominant process. And if pair production becomes the predominant process of interaction, then it will result into differential absorption. Similar to we have seen in photoelectric effect, which means that then there will be a differential absorption in body, there will be a shielding effect of bone, and tumor will not receive adequate dose of radiation. So that is the reason that all the commercially available linear accelerator work at an energy less than 20 MeV radiation. So to summarize, the photoelectric effect is the dominant process of absorption in diagnostic radiology. Compton effect dominates in therapeutic radiology. Now, as a result of these interactions, that is Compton process, photoelectric process, pair production, what actually you get? What is the end product? End product is fast-moving electron. Now, these fast-moving electrons, then they will move inside the body and will bring chemical and biological changes. So these type of radiations, which first produces fast-moving electron, and then these fast-moving electron causes all the biological damages, are known as indirectly ionizing radiation. Now, there are directly ionizing radiations also. They are basically the charged particles, like alpha particles or proton particles, and they directly damages the biological matter. So they do not work by first ejecting the electron. No, they directly damaging the biological material. While indirectly ionizing radiation, they first produce the fast moving electron as a result of this interaction, and then these electrons will cause all the biological damages. Now, coming on to the mechanism of action, again, I will not go into detail. The critical target is DNA molecule. We know that cell contains nucleus. In the nucleus, we have chromosomes on which the DNA molecules are present. And DNA is a double helical structure. If you look at the DNA structure, there are two helix, and these two helix are held with each other by a chemical bond. And there are bases present on these helix. Usually there are four bases: guanine, cytosine, thymine, and adenine. And there is a fixed pattern of pairing between the bases. So and so that guanine will always pair with cytosine. The thymine will always pair with adenine. Now, what are the evidence which suggest that DNA is the target for radiation to act? There are plenty of evidences available in the literature. I have just chosen two evidence to show you here. Now, this is an experiment where this fern spore is bombarded with alpha particle. Now, the beauty of this fern spore is that nucleus is eccentric. So in this experiment, the spore is bombarded with alpha particle, but the nucleus is protected by an aluminum foil. So when you put the aluminum foil in front of nucleus and bombard with alpha particle, it has been observed that germination took place. But when you remove this aluminum foil and again bombard this spore with alpha particle, they observed that germination did not take place. It clearly indicates that something inside the nucleus, which is very vital, is important target for radiation to act. And we know that most vital part in the nucleus is a DNA molecule. Similarly, this is again, a parasitic wasp egg. Here also the nucleus is eccentric. The same experiment is repeated here. You bombarded this egg with aluminum foil in front of nucleus. They observed that hatching took place, but when you remove this aluminum foil and bombarded with alpha particles, they found that hatching did not take place. So this again gives you an idea that something very vital inside the nucleus is responsible for radiation to act. Now, coming on to the mechanism of action, we all know that two type of actions are there. One is indirect, the other is direct. Now, in direct action, there is a direct damage. The radiation will directly damage the DNA molecule. But in indirect action, radiation first interact with the water, and then it causes a free radical formation, and then this free radical formation will damage the DNA molecule. So what happens that first this electron, the fast moving electron or the charged particle, they will eject one electron from the water molecule. As a result, you have an ion radical. Now this ion radical is highly unstable. It dissociates into an hydrogen atom and a free radical, and this free radical, the hydroxyl radical, this is highly reactive. This will react with DNA molecule, will break the chemical bond, unwind the DNA structure, and ultimately result into cell death. Now, important point here is that lifespan of this free radical is very, very short, that is 10 power minus 5 seconds. So only free radical which are formed in a radius of 3 nanometer around the DNA molecule are able to act on DNA molecule. If free radicals are formed beyond this point, then what happens that by the time it reaches to DNA molecule, its timeline is over. So it will not be able to act on DNA molecule. So just to summarize that, first we have a physical interaction. As a result, you have fast moving electron, and then this fast moving electron will ionize the water molecule. As a result, you have ion radical. So this is an ion radical which is highly unstable, dissociate into hydrogen atom and free radical, and then this free radical will cause the biological effect. So same thing here in a diagrammatic way, that in indirect action, photon, there is a physical interaction. This electron will ionize this water molecule. As a result, you have free radicals, and then this free radical damages the DNA molecule. In direct action, this electron itself causes the direct damage to the DNA molecule. So this indirect action is seen mainly in low LET radiation, while direct action is seen with high LET radiation. Now, if you look at the timeline of various physical and chemical process, it is very, very short, but biological changes may take hours to decades, which I will discuss in a short while. If you look at the number of damages per gray, it is around 1,000 to 2,000 base damages, single strand break around 500 to 1,000, double strand breaks around 40 to 50. Now, another important point here is that radiation-induced cell death is usually a delayed phenomena. It does not appear or it does not occur immediately. In fact, if the cell is exposed today, it may take few days for the cell to die. So it is a slow process. It is a delayed phenomena. In fact, cell may undergo few cell division after exposure, depending upon the dose of radiation before it dies, right? So this kind of death is known as mitotic death. Another type of death which is seen in few cells like oocytes, lymphocytes, salivary gland, and oligodendrocytes is known as interphase death. This is usually more rapid death. It occurs between 4 to 24 hours, and this occurs through apoptosis, which is a programmed cell death. Now, again, very interesting, what happens or how this radiation damage to the cell is manifested clinically. Just very interesting, just try to understand. Now, if there's an exposure of the cell, then this cell may take one of the three pathways. One, there may be single strand damage, but it may get repaired and you see nothing will happen. So there will be no, no clinically detectable changes. Or there may be a lethal damage. As a result, the cell will die. But as I said, it is a slow process, so it will take few days to weeks for cell to die. And how it is manifested clinically, depending upon number of cells which are affected. If small numbers of cells are killed, then there will be transient radiation injury, but it will be healed. If there is more number of cells are killed, then there will be, prolonged radiation injury symptoms, but again, it will be healed. But if large number of cells are killed, then organism will die or it will perish. The third pathway is that there is a single strand break. It may get repaired, but it is misrepair. And this result into mutation. So if mutation is in somatic cell, then it is manifested clinically in the form of cancer formation. But we all know that this will take few years for Dr. Deepa, have I lost the correction?
Yes, sir, we lost connection.
Okay, I am again sharing. Now can you see, Dr. Deepa?
Yes, sir.
Okay. So this is evident from the survivors of Hiroshima and Nagasaki that after many years there was sudden spurt in the cancer, among the survivors of the Hiroshima and Nagasaki. Similarly, genetic defects were seen in the next generation of the survivors of bomb blast. Now, point which I am trying to make here is very, very important. Radiation injury is different from other physical injury in a way that it takes few days to weeks to years to generation for radiation injury to manifest clinically. While other injuries, other physical injuries are manifested immediately. If you have a cut wound, it is manifested immediately. If you have a bullet injury, it is manifested immediately. But radiation injury will take, up to generation to manifest. So as a radiation oncologist, you have to be very, very responsible when you use radiation for treatment purpose. And you have to keep this point in your mind that you may do some mistake today, it may not be manifested immediately, but it may cause harm to that particular patient, maybe after years or maybe after generations. So you have to be very, very careful while using radiation in medicine. So radiation injury is different from other physical injury. I think I have emphasized on this point. Another important point is that radiation only kills dividing cell. It does not kill resting cell. Exceptions are there like oocytes and lymphocytes when it also kills the resting cells. Another important point is that higher the multiplication, more the cell death. And next point is that cell death usually occurs after few cell division. In fact, when cell attempts to multiply, only then radiation injury or radiation death will take place. Now, this gives rise to law of Bergonie and Tribondeau. According to this law, the radio sensitivity of population of cell is directly proportional to their reproductive activity and inversely proportional to their degree of differentiation. So what does it mean? It means that cells are more radiosensitive if they are rapidly proliferating, if they are immature cells, or if they are poorly differentiated cells. This is a spectrum to show you from most sensitive to least sensitive cells. Most sensitive are rapidly dividing cell like a small intestine, bone marrow, etc. Least affected cells are slowly dividing cell like brain, nerves, etc. Now coming on to the cell cycle, we know there are 4 phases of cell cycle, the G1, S, G2, and M. So in G1, the protein synthesis for DNA takes place. In S phase, DNA synthesis takes place. In G2 phase, the protein synthesis for RNA takes place, and RNA also synthesized here. And finally, cell goes to mitotic phase, which is further divided into 4, prophase, metaphase, anaphase, telophase. And in this, part, the cell divide into 2 cells from 1 cell. Now, important point here is that timeline of various phases in different cells are almost similar except in G1 phase, which is variable. So the timeline in G1 phase is variable in different type of cells. As I said, I'm not going into detail. I just want to refresh your knowledge so that it helps you in understanding the radiobiology from next module. Now, there are checkpoints also. The important checkpoints are two. One is at the end of G1, other is at the end of G2. Now, what is the purpose of these checkpoints? Now, these checkpoints basically, what happens that cells are arrested here. And whatever new DNA protein, has been formed, this is basically checked here, whether DNA which are formed or the new DNA which have been formed, they are correct or there is some defect. And if there is a defect, then this defect is repaired. And once the body is satisfied that now there is no more defect in the newly formed DNA, only then cells are allowed to pass on to the next phase of the cell cycle. So in a way, a kind of proofreading is done here. And if there is any mistake, then that mistake is corrected. And only then cells are allowed to move on to next phase of cell cycle. Now, these are the stalwarts and father of, radiology, radiation biology, radiation oncology. Purpose of projecting their picture is just to pay tribute to all of them. All of them are great, personalities. Now, coming on to the radiation damages in the cells. There are mainly two types of damages. One is called lethal damage. The other is called sublethal damage. The third type of damage is also there, that is potential lethal damage. So again, very briefly, I will discuss all these things in detail in radiobiology modules. So very briefly, now in lethal damage, what happens, it is considered that DNA is the target and two strands of DNA molecules are two critical sites. So what happens that as a result of radiation, single radiation event, both the critical sites are damaged and this result into cell death. In sublethal damage, what happens that as a result of one radiation events, only one critical site is damaged, causing sublethal damage. If in a short interval, as a result of another radiation event, another critical site is damaged, causing another sublethal damage, then interaction of these two sublethal damage will okay. So now am I audible?
Yes, sir, you're audible.
I'm losing connection in between. I don't know, but anyway, not much interruption. So
We were in the sublethal damage.
yeah. So basically, this is the normal DNA molecule. Now here, what happens that if if there is a single strand break, so this is basically repaired using opposite helix as a template. So it gets repaired. Or if there are double strand break, but two breaks are away from each other, then they behave like two single strand break. And again, these break can be repaired using opposite helix as a template. But if two breaks are very close to each other or opposite to each other, then it results into cell death. Then second theory.
Sorry to interrupt you, sir. Sir, we just missed the last portion of that potentially damage in the previous slide, sir. Yes.
So I covered this, the sublethal damage or not?
Sublethal damage was covered, sir. When
Okay. So sublethal damage, basically I have covered. So basically I told that, if there is sufficient gap between these two radiation events, then this sublethal damage may be repaired. And this is called repair of sublethal damage. Now the question is that how this sublethal damage is repaired. So there are two theories of repair of the sublethal damage, that is template theory and chemical pull theory. And I think I have described these. Dr. Deepa, can I go on to the next slide?
yes, sir, we can.
So I have already described this slide. So chemical pool theory is another theory for repair of the sublethal damage. Now, according to this theory, there are some entities inside the cell, and these entities are basically the enzymes which can repair the DNA damages. So what happens that suppose in this cell, there are 500 entities or 500 enzymes which can fix up the DNA damages. And suppose cell is exposed to 10 red, and these 10 red result into 5, sublethal damages or 5 damages. Now, or causing 5, damage. So, and suppose each damage require 20 enzymes for repair. So total enzymes required to repair 5 damages are 100. And how many we have? 500, which means that repair will take place. But if the radiation result into damage to 100 sites, and we know each site will require 20 entities for repair. So the total enzymes will be 2000, which are required now to repair 100 sites. And how many we have? 500, which means that cell will not be repaired or damages will not be repaired, and this will result into cell death. So in fact, this chemical pool theory defied two target theory, which I just described in my previous slide, because it says that there are multiple targets in the cells and the number can be anything more than 1. So we denote it as n number of targets. So n can be anything from 2 to 10, 20 or 100. Now, if n minus 1 target hits, then repair will occur. And in order to bring death, all the n targets should hit. Now, coming on to the potential lethal damage, that is a third type of damage. Now, this is very interesting, kind of damage. Now, it is primarily a lethal damage. But if we change the post-irradiation condition in such a way that there is a lack of nutritional supply or lack of oxygen supply, then it will not result into cell death, rather the damage will be repaired. So that is called potential lethal damage. I again repeat, in normal circumstances, this kind of damage will always be lethal. But if we manipulate and change the post-exposure condition in such a way that there is a lack of nutritional supply or lack of oxygen supply, then there will be repair. And that is why we call it potential lethal damage, which I hope I am clear to all of you. And why there will be, repair of this damage when there is lack of nutrition and oxygen supply, because suboptimal condition will not allow cell to divide. And I told you that radiation will only act when cell attempts to multiply. So when cell will not be able to divide, then body will enough time to repair this damage. Now, clinical significance is that if patient is malnourished and anemic, which lead to deficient nutritional and oxygen supply, which will result into repair of this damage. So cell death will decrease, and hence there will be poor response of tumor to radiation. Similarly, if tumor is very large and necrotic, again because of deficient oxygen and nutrition supply, there will be less damage or there will be repair of the damage. This will result into poor response. In fact, many drugs have been tried experimentally, which will check the repair of potential lethal damage. They have shown good result in laboratory, but when they tried clinically, they have not shown to be effective. But remember that repair of potential lethal damage does not take place with high LET radiation. So in malnourished patient, high LET radiation is probably better. And here I just finished my first module. I will directly go to my second module, which is primarily our, area of interest. That is, the real radiobiology, which I will start from second module, and we can have question from audience at the end of the presentation. And as I told you that in first module, I did not go into detail of these various concepts, because I presume that all of you already been taught by your medical physicists about all these things. But my purpose was just to refresh your knowledge so that you can understand radiobiology now in a better way. Now remember, cell survival curve. I will start with the cell survival curve. Now cell survival curve is considered to be the most difficult part of radiobiology. But remember that if you understand cell survival curve, you will understand almost 2/3 of the radiobiology, because most of our radiotherapy principles are based on cell survival curve. And I can tell you that cell survival curve is not very difficult. Only thing I need from all the participants is attention and focus on the screen. I try to make cell survival curve very, very simple. Just focus on the screen. So let me start. Now there will be, these terms which I will be using very frequently during my presentation, like exponential relationship, single hit event, multiple hit event, which is equal to double hit event, semi-logarithmic graph, or D10 and D0. I want all of you to understand clearly all these terms and memorize these terms. These are very, very important. Now, what do we mean by clonogenic cell? Now, clonogenic cell means that a cell which is capable to proliferate indefinitely and form a large colony from a single cell, then this cell is said to be clonogenic. What we mean by cell death? Now, meaning of cell death is different for different type of cell. For proliferating cell, loss of capacity for sustained proliferation is considered as cell death, which means loss of reproductive integrity, which means that cell may survive, but if it has lost its capacity for sustained proliferation, then we call it cell death. And for this, we need around 2 gray of radiation. For differentiated cells, loss of specific function is considered as cell death. And for this, we need a very high dose of radiation, that is 100 gray. Can you think of any situation where we want cell to lose its specific function? Any clinical situation can you think of? The clinical situation is one of that is trigeminal neuralgia. And we know we give very high dose of radiation, maybe 60, 80, or maybe 100 gray, and that too in a single fraction. So for this purpose, we need to deliver very high dose of radiation. Now, as I mentioned, that following irradiation, cell may still be surviving, cell may still be intact, or may be able to produce protein, or may synthesize new DNA, or even may go few cell division. But if it has lost the capacity to reproduce indefinitely, then it is considered as cell death. Now, what is cell survival curve? Now, a cell survival curve is a graphical representation of the fraction of cells surviving to a given dose of radiation. And this graph is obtained by plotting the dose along the linear x-axis and surviving fraction along the logarithmic y-axis. So I have used two terms here, the logarithmic scale and linear scale. So what are these two kind of scale, logarithmic and linear? Just try to understand. On the left panel, linear scale, on the right panel, logarithmic scale. Now, concentrate on the left panel. Now, in linear scale, same quantities are represented by equal distance. So what happens in this scale, you see that between any 2 points, the same quantities are represented, whether between these 2 points or between these 2 points or between these 2 points. And the distance between all the points are also equal as reflected by similar height of this arrow. So in linear scale, same quantities are represented by equal distance. Now focus on the logarithmic scale on the right panel. Now here, increasing quantities are represented by equal distance. So here what happens, you see the distance between the 2 points are equal as reflected by same height of the arrow, but the quantities which they represent are different and in some pattern. Now you see between these 2 points, it represents 10, it represents 90, 900, 9,000. So similar, increasing quantities are represented by equal distance. So then we call it logarithmic scale. And I hope that now you can differentiate between the linear scale and a logarithmic scale. What is semi-logarithmic scale? You join the two scales, then you get a semi-logarithmic scale. So in semi-logarithmic scale, on one axis, you use logarithmic scale and it is used along the y-axis and it is used to denote the survival fraction. On x-axis, you use a linear scale just to show you that it is semi-logarithmic because distance between the points are equal, but it is representing increasing quantity. On x-axis, you use linear scale. So this is used to denote the dose of radiation. So this is linear scale. You can appreciate that distance between the 2 points are equal and the quantities which they are denoting are also same. So when you combine the two types of scale, then we call semi-logarithmic scale. I hope you understand what we mean by semi-logarithmic scale. And remember that all cell survival curves are plotted on a semi-logarithmic graph, right? How we obtain a cell survival curve in laboratory? Very simple. If you have radiobiology lab, you can generate cell survival curve. What we do basically, take a tumor, chop it into small pieces, treat these pieces with the enzyme trypsin to make a single cell solution. Now take out these cells, count them and put them on Petri dish which contains culture media. Incubate for 1 to 2 weeks, and at the end of 2 weeks, you will observe black dots which very little differ in size. Now these black dots you can see by your naked eye. Now these black dots are basically the colonies which have been formed from each cell which you put here on Petri dish. But interesting point here is that if you count these colonies, the number of colonies are always less than number of cells which you put on the Petri dish. Why it is so? Because some of the seeded single cells are still single. They are not able to form the colonies. Some cells, they die an apoptotic death. Some cells have managed to complete 1 or 2 divisions to form a tiny abortive colony. Again, you are not able to see them. But majority of the cells will have grown into a large colonies. And as I said, they differ very little in shape and size. And actually, these are the cells which are said to have survived because they have retained their reproductive integrity and they are able to form colonies. So naturally, when number of colonies are going to be less than number of cells seeded, then it means that you need to know the plating efficiency of the Petri dish. So what is plating efficiency basically? It is basically the efficiency of the Petri dish to form colonies from non-number of seeded cells. And it can be defined as percentage of cells seeded that grow into colonies known as plating efficiency. And it can be obtained from this formula, that is number of colonies counted divided by cells seeded multiplied by 100. For example, if you put 100 cells in a petri dish, incubate for 1 to 2 weeks, and number of colonies counted 90, then what will be the plating efficiency? Just put these value here. So 90 is the colonies counted, 100 is the cell seeded, and to get a plating efficiency multiplied by 100, so you get 90% plating efficiency. And once you know the plating efficiency, then with this formula, you can find out the survival fraction. So it is basically the colonies counted divided by seeded multiplied by plating efficiency. So now coming on to how exactly we get a cell survival curve in laboratory. So to generate a cell survival curve, you need two parameters. One is increasing dose of radiation. Other is reducing survival fraction. How do we get these parameters in laboratory? So what you do, take a petri dish, put 100 cells, incubate for 1 to 2 weeks, and after 2 weeks count the colonies. Suppose 90 colonies are counted, then you can find out the plating efficiency, 90%. Now you take other petri dish, like I have taken 3 petri dish here, put increasing number of cells in these petri dish, irradiate with increasing dose of radiation, and then incubate for 1 to 2. And after 2 weeks, again count the colonies. Suppose number is 72, 30, and 45. So now with this formula, you can calculate the survival fraction. So if we calculate the survival fraction for first petri dish, colonies count 72, colonies seeded 400, and plating efficiency is 0.9. Second petri dish, colony counted 36, seeded 1000, plating efficiency 0.9. Third petri dish, colonies counted 45, seeded 10,000, plating efficiency 0.9. And when you calculate, it comes out to be 0.2, 0.04, 0.005. So now you have both parameters, that is increasing dose of radiation and reducing survival fraction. Take a semi-logarithmic graph, put these values here, join them, and you get a cell survival curve. So very simple, right? Only thing, you need a radiobiology lab in your department. So after obtaining the cell survival curve in laboratory, now we will study the cell survival curve first of microorganisms like bacteria, and then we will move on to cell survival curve of mammals or of human beings. Now remember that for bacteria or microorganisms, the cell survival curve is a straight line on a semi-logarithmic graph. Now you may get many information from this graph. One is that if you know one parameter, you can find out the other parameter. For example, if you want to know what is the survival fraction at 3 gray of radiation dose. So what you do at 3 gray, draw a vertical straight line upward. Where it meets on the curve, draw another horizontal line on the survival fraction. And where it meets, this figure gives you the survival fraction. So after 3 gray, 37% is the survival fraction. Similarly, after 7 gray, repeat the process and you get the answer that after 7 gray, 10% is the survival fraction. Or the other way around, if you know the survival fraction, you can find out the dose at which this survival fraction result. For example, if you want to know what will be the dose of radiation which result into 1% survival fraction. So now repeat the same process in the reverse direction. Draw a horizontal line, straight line where it meets on the cell survival curve, draw a vertical line on the dose, and it will give you the answer. So 1% will be result of 13 gray of exposure. I hope it is clear. Now, another important point or another important information which is more important than the previous information is this, that slope of the curve represent the radiation sensitivity. This is very, very important. Remember, steeper the curve, more sensitive is the cell line. Shallower is the curve, less sensitive is the cell to the radiation. Here I have taken two cell line cell survival curve. On the left panel, it is more sensitive as the curve is steeper. On the right side, it is less sensitive as the curve is shallower. I will prove it here. Now, if you just focus on the left side, after 5 gray, you have 20% survival fraction, which means 80% of the cells are killed here. Now on the right panel, same dose 5 gray will reduce survival fraction to 70%, means only 30% are killed here. Naturally, we will say this is more sensitive cell. Similarly, after 10 gray, the survival fraction reduces to 5%, which means 95% of the cells are killed here. Now on this side, 10 gray will reduce to 30%, which means only 70% cells are killed here. So again showing that this is more sensitive than this. Or if you want to reduce survival fraction to 5% here in this cell line, then you have to deliver more than 20 gray. While the same endpoint you are getting at 10 gray. So this again shows that this cell line is more sensitive than this cell line. I hope I am clear now. So one important message which I want all of you to remember and engrave on your brain, that steeper the slope, higher the sensitivity, and vice versa. So this is a very important point which I want all of you to remember. Third point, remember that if you plot the cell survival curve on a normal graph, then how does it look like? It looks like something like this. It is a sigmoid shape curve on a normal graph, not on a semi-logarithmic graph. And you are observing a very important finding here, that as the dose increases, the curve gets parallel to the horizontal axis, which you can see here. And similar kind of curve we have seen in the previous module, where we saw that in when we discussed the attenuation is an exponential function, which means that this line will be just parallel to horizontal line, which means that survival fraction can never become 0. Why it is so? Because as I said, that similar kind of curve we have seen in previous module also, and the reason was that there was an exponential relationship. Only then we get this kind of curve. So we can say that survival fraction is an exponential function of dose of radiation. Now again, I will discuss exponential relationship in detail, because this is very, very important. Once you understand this, I think cell survival curve becomes very simple. Now, before I go to that, let me tell you that probability of cell killing or surviving is a random phenomenon. Now, try to understand. Now here, I am showing the 100 cells, and these 100 cells are exposed to 4 centigrade. And let us presume that each centigrade is capable, like a bullet, to kill 1 cell. So if you are delivering 4 centigrade, or I say 4 bullet, then you will kill 4 cells. If you double the bullet or the dose from 4 centigrade to 8 centigrade, you will be able to kill 8 cells. If you further double the dose, then you will be able to kill 16 cells. If you just look at the relationship on a graph, more the bullet, more the number of cells killed. So this relationship is a linear relationship. But this is only a hypothetical relationship. Practically, it does not happen, because the cell killing is a random phenomenon. Practically what happens? Try to understand again. If 4 bullets of 4 centigrade kills 4 cells, so when you double the dose from 4 bullet to 8 bullet, what happens? That some of the cell is hit by 2 bullets and some of the cell by single bullet. We know that one bullet is sufficient to kill one cell, but because of random nature, some of the cells are hit by 2 bullets, which means that 1 bullet is going waste. And that is the reason that instead of 8 cell dead, you will have 6 cell dead. When you further double the dose of bullets or of dose of radiation from 8 to 16, what will happen? That some of the cells will be hit by 3 bullets, some by 2 bullets, some by single bullet, which means that now more bullets are going waste. We need a single bullet to kill a cell. Some cells are hit by more than 1 bullet. So again, instead of having 16 cells killed, you will have 10 cells killed. And now if you look at the relationship, so let me just first show you the hypothetical relationship when there was a linear relationship, which means if you have 2 bullets, 2 cells killed, 4 bullets, 4 cells killed, 8 bullets, 8 cells killed. But we know because some of the bullets are going waste, so the curve is tilted towards horizontal axis, which means that when you double the bullets or the dose of radiation from 2 to 4, so instead of 4 cell kill, you will have 3 cells killed. Similarly, when you further double the dose from 4 gray to 8 centigrade, then instead of 8 cell kill, you will have 6 cells kill. So another important information is that dose of radiation goes waste because of random nature of hit to the cells. Now let me take a bigger picture. We have 100 cells, we have 100 centigrade dose of radiation. So these 100 cells are exposed to 100 centigrade. Now what will happen? Because of random nature, some of the cell will be hit by 2 bullets, some by single bullets, some by 3 bullets, and some by 4 bullets. And some of the cells will not be hit at all. So 100 bullets can kill 100 cells, but because of random nature, some of the cells will not be hit at all. And some of the cell will be hit by more than 1 bullet. Now let me give you, I always give a very, very, very interesting analogy. Suppose you have 100 people who are involved in antisocial activities. The police basically, finally decide that we should fire to this mob of 100 people. And suppose they fire 100 bullets. We know that to kill a person, we need just single bullet. But if you fire 100 bullets to 100 people, do you think that all the 100 people will be killed? Answer is no, because we know that some of the person will receive more than 1 bullet and some of the person will not receive at all any bullet. So same thing is happening here at the cellular level, that some of the cells are hit by more than 1, some of the cells are not hit at all. So with this background, let me now go to explain the exponential reduction in survival fraction. Very important slide. I would again, suggest you to concentrate on the screen. Suppose you have 1000 cells, irradiate to 100 centigrade, and this result into reduction or survival of 100 cells. So 1000 cells irradiate to 100 centigrade and 100 cells now survive. Now these are the 10% of 1000 cells. So this dose of radiation is called D10. So now we may define D10. D10 is the dose of radiation which reduces the survival fraction to 10%. And then we call it 1 exponential or log reduction in survival fraction. And this is denoted like exponential power minus 1. Now these 100 cells again exposed to 100 centigrade again, which is another D10, because we know 100 centigrade is D10. And D10 will reduce survival fraction to 10%. So now 10 cells are survived. And we can say that survival fraction has been reduced to 2 log reduction or 2 exponential reduction. Now these 10 cells again exposed to another D10, 100 centigrade, and D10 we know will reduce survival fraction to 10%. So now 1 cell will survive, and we may call that survival fraction has reduced to 3 exponential reduction. So I hope you understand what is D10. Now, just observe that similar increment in dose result into similar percentage reduction in survival fraction, but not in absolute number. After first D10, you have 100 cells survive. After another D10, you have 10 cells survive. But in percentage wise, it is similar. And if we have this kind of relationship, we call it an exponential relationship. That similar increment in one parameter result into similar percentage reduction in another parameter, but not in absolute figure, then we call it exponential relationship. You can, same thing you can see in reference of cells killed. Now D10 will kill 90% of the tumor cells. So after one D10, 900 cells are killed. After second D10, 90 cells are killed. After third D10, 9 cells are killed. But every time 90% of the cells are being killed. So again, similar increment will result into 90% cell kill, but in absolute term, it will be different. So I hope now, I think you must understand what we mean by exponential relationship. So each increment in dose will reduce the survival fraction by same proportion and not by the same number. And this relationship is called the exponential relationship. So we can say that survival is the exponential function of dose. And remember, when there is an exponential relationship, then the parameter can never become zero, similar to intensity of radiation beam. And I hope now that exponential relationship should be very clear to all of you. Now in this, so previous slide, I took 1,000 cells to start with. Now I will take 1 cell to start with. So after first D10, you know, after first D10, there will be one exponential reduction, means 10% will survive. So 10% of one cell is 0.1. After 2D10, 2 exponential reduction, means 10%, 10% or 0.1, 0.1, that is 0.01, which means that 0.01 cells survive and 0.01 is 10% of 0.1. After 3D10, 3 exponential reduction, which means 0.1, 0.1, 0.1, so 0.001 and 0.001 is, 10% of 0.01. Okay, so after understanding or explaining D10, now we will understand D0. What is D0? So we already now have a clear idea that D10 is the dose required to reduce the survival fraction to 10%, and then we call it one exponential reduction. Now D0 is the dose required to reduce the survival fraction to 37%. And then in reference to D0, we call it one exponential reduction. When in reference to D10, when it reduces to 10%, then we call one exponential reduction. In reference to D0, when 37% are survived, then we call one exponential reduction. So for the time being, just forget about D10. Let us concentrate on D0. So D0 is the dose required to reduce the survival fraction to 37%, and then we call it one exponential reduction. So naturally 2D0 will reduce to 2 exponential reduction, that is 0.37, 0.37. 3D0 will reduce to 3 survival fraction, 0.37, 0.37, 0.37. And from this, we can derive a formula that survival fraction is equal to exponential power minus D upon D0, where D is total dose of radiation and D0 is dose which reduces the survival fraction to 37%. So this is not very complicated. This is very simple. Just I will explain in next slide. So this is the formula which we derived, right? And so if the total dose, just try to understand, is 1D0, then putting this value here, then after 1D0, survival fraction will reduce to 1 exponential reduction. And this is what we saw here, that 1D0, 1 exponential reduction. If the total dose is 2D0, then putting this value here, you get a survival fraction E minus 2. And this is what I said in previous slide, The 2D0 means 2 exponential reduction. Similarly, if it is 3D0, then 3 exponential reduction. If it is 10D0, then 10 exponential reduction. So this formula is needed just to calculate very fast. Otherwise, from on these steps also you can calculate, but this is time consuming. I hope now you understand this formula.
Sir,
yes.
There is one doubt why 37% is chosen.
37%, right? So
yes.
This is all basically experimental, observations. It's all experimental observation, right? So these values are basically derived, on laboratories, on experimental, on cell lines, right? And we basically apply these information to clinical settings. So after 1D0, you have 37% surviving. After 2D0, 0.37. After 3D0, 0.337. Now, more important than this is the question that why we are interested in D0, right? Why we are interested in D0. Now, why we are interested? Because D0 is called mean lethal dose. Mean lethal dose is the dose of radiation which is capable of producing one lethal event per cell, which means that 100 centigrade should kill all the 100 cells. If you call D0 is 100 centigrade, it means that if 100 cells are treated with 100 centigrade, all the cells should be dead. But because of random nature, which I explained, some of the cell will always be surviving. So that is why D0 term has been taken. D0 theoretically should reduce the survival fraction to 0 level, but because of random nature, some of the cell will always survive. So that is the reason why we are interested, or why we call it D0. If you look at the relationship between D0 and D10, if I ask you which one is bigger, which one is higher, naturally D10 will kill 90% of the cell. D0 will kill 63%. So D10 should be higher. So relationship is D10 is equal to 2.3 D0. Now, mean lethal dose, or the D0 for mammalian cells for X-rays, are usually between 1 to 2 gray, and number of DNA lesions per cell, after a D0 dose of radiation are base damage more than 1,000, single strand break 1,000, and double strand break 40. Now, these are the D0 level of some of the organisms. Virus, E. coli, and mammalian cell is usually 1 to 2 gray. If I ask you which one is most sensitive cell, answer is naturally number 3, that is mammalian cell, because for virus to kill 63% of the cells, you need 1500 gray, very high dose of radiation, while for mammalian cell, you will require just 2 gray. I hope now you understand about the D0. Now, survival fraction is an exponential function of dose of radiation. We already discussed in a mathematical way. Now, same thing I will try to explain on graph. Now, this is the cell survival curve of bacteria. So what I'm going to do, I am going to, give an equal increment on the dose level. And you will see how survival fraction is going down. So just look at the screen. I'm giving equal increment and how the survival fraction is going down. So these are the equal increment in the dose because the width of the bar are exactly same. And you see there is similar percentage reduction in the survival fraction as reflected from the height of these arrow. So you can see, and since every time you add, another increment, the survival fraction reduces to 10%. So each increment is 1D0, or sorry, 1D10. So this is 1D10. After 1D10, you have 1 exponential reduction. After 2D10, you have 2 exponential reduction, 3 exponential reduction, 4 exponential reduction. So from the graph also, if similar increment in the dose result into similar percentage reduction in the survival fraction, then you can say that there is an exponential relationship. So the message is very important, which I again want all of the participants to remember, that if a cell survival curve is a straight line on a semi-logarithmic graph, then it represents an exponential relationship. If it is curvy, anything from the straight line, which is away from the straight line, then it does not reflect an exponential relationship. So this is a very important message which I am trying to give to all the participants. Now, same thing in reference to D0, same thing. So I'll just go fast. Similar increment, and reduces survival fraction to 37%. So naturally, each increment is called D0. So again, 1 exponential, 2, 3, and 4. But message again, I would like to emphasize that similar increment, if you get a straight line on a semi-logarithmic graph, then it reflects an exponential relationship. If it is a curvy, then it does not show an exponential relationship. So kindly remember this very important message. Now with these background, let us move on to mammalian cell survival curve, and it is obtained from HeLa cells of human cervical cancer and hamster cell from the lung of newborn of Chinese hamster. So I think now we are very clear about the cell survival curve of bacteria, and it is very simple, a straight line. Had it been same for the mammalian or for the human being, I think the radiobiology would have been very, very simple. And by this time, your radiobiology would have finished. But we know that God always believed in making the things complicated for human being, and exactly God did the same thing in cell survival curve also. And it is seen that for mammalian cell, it is not a straight line from the very beginning, but initially there is a curvy line. After that, it is a straight line. And this curvy line brings all the complexity in mammalian cell survival curve. We'll try to understand those complexities. Now, so mammalian cell survival curve got two portions. One initial portion, which is a curvy, there is a continuous bending portion. And this is seen in the low dose region. Till it reaches to some point B, after that, so naturally if it is a curvy portion, so if you remember what I said, it does not reflect an exponential relationship. Now after this point, there is a straight line, which is seen in high dose region. So when it is a straight line, naturally it shows that there is an exponential relationship. So initial portion is not exponential. Terminal portion is exponential. Initial portion is seen in low dose region. The exponential portion is seen in high dose region. Now, initial portion is not exponential. We'll try to show you on cell survival curve for mammalian cells. As I said, it is a continuously bending, so it's a curvy portion. Now, again, I will do the same thing. I will make the similar increment on the dose region, and you will just observe what's happening on the survival fraction. And just to compare, on the right hand side, I have taken the cell survival curve of bacteria. Very simple, just try to understand. Now, after 1 D10, you see if there is any reduction in the survival fraction. There is no gap, which means there is no reduction in survival fraction. Ideally, D10 should have killed 90% of the tumor cell, but there is no reduction, no tumor cell kill. While here you see, if there is a straight line, right from the very beginning, there is a 90% cell kill. Now, another D10, there is some reduction in survival fraction, but not up to 10%, which means ideally D10 should have killed 90% of the tumor cell, but it is killing only say 10%. While here, again D10, 90% tumor cell kill, 10% reduction, or reduction of survival fraction to 10%. Keep on giving increment on left hand side. What are you observing? You're observing that there is a similar increment every time D10, but reduction in survival fraction keeps on increasing till it reaches to 10%, which means percentage of cells being killed keeps increasing till D10 is now able to kill 90% of tumors. And after that, this is a straight line. So again, you give similar increment in the dose region, similar percentage reduction. So straight line, exponential relationship, but here, when you give the increment, the reduction in survival fraction keeps on increasing till it reaches to 10%. I hope I am clear. So we can say that with the same increment in D10, the survival fraction keeps increasing till it reaches to 10%. And this is what D10 is meant for, that it will reduce survival fraction to 10%. But initially, it is not reducing to 10%. So we can say that in low dose region, the efficiency of radiation to kill cell is reduced. So this is the basically message which I am trying to give to you, that in low dose region, the efficiency of radiation to kill cell is reduced. D10 should have killed 90% of tumor cell, but it is killing less than 90%. Or we can say that in shoulder region, radiation goes waste. So in mammalian cell survival curve, in low dose region, the relationship is not exponential, and this portion of the curve is called shoulder, while beyond point B, same dose increment result into equal reduction on survival fraction. So in terminal portion, the relationship is exponential. Or I can say that shoulder basically reflect waste of radiation dose. If there is no shoulder, a straight line, then there is no wastage of radiation. And efficiency of radiation to kill cell is more. For example, in alpha particle, if you treat cells with alpha particle, there is no shoulder. It is a straight line from the very beginning. So in low dose region, relationship between survival fraction and dose of radiation is not exponential. In high dose region, the relationship is exponential. In low dose region, the efficiency of radiation to kill the cell decreases. I hope the messages are very clear. If you look at the shape of the cell survival curve for different cell line, it will be different. Some will be like this, some will be like this, some will be like this. And if you observe carefully, the terminal portion does not differ. It is almost same, a straight line. The difference lies only in the initial portion. Some of the curves or some of the curve are more curvy, some of the curves are less curvy. Now the question is that why mammalian cell survival curve consists of two portions, why it is not exponential from the very beginning. I think there are various models which have been put forward to explain the cell survival curve or the mammalian cell survival curve. But as a radiation oncologist, I will just confine myself to explain these two models, the multi-target model and the linear quadratic model, because multi-target model is important for your examination. Sometimes it is asked, and linear quadratic model is, why it is important, because every day in our clinics, what we practice is based on linear quadratic model. So that is why it is very, very important to understand linear quadratic model, not only for examination, but for practicing a good radiation oncology. So these two models I will discuss, and I think it's already 7:30. So Dr. Deepa, I think I was otherwise planning to finish this module today, but I think already it's 7:30. So I must stop at this point, and we will discuss these two models afresh tomorrow, because again they need a fresh mind. So I know that already the participants are must be tired mentally, especially not physically. So I think I must stop at this point. And if there is some question, and let me explain before I take questions, because let me tell the participant that I'm not a medical physicist. So I will, if you are asking question on medical physics, I may not be able to explain everything. Similarly, I'm not a cell biologist. So if you are asking any question or any question on the cell biology, again I will not be able to tell you. But yes, question related with clinical radiobiology, certainly if you have any, we may take here. So Dr. Deepa, over to you.
So there was one question from the module 1 regarding the oxygen fixation theory. Like if considering the oxygen fixation theory, can we combine anti-angiogenesis therapy and radiotherapy? So
basically, let me tell you that all these questions I will take when I will go to the clinical part of radiobiology. So far, I'm just trying to explain the cell survival curve. That's it. So from the third modules onward, all the clinical application will come. We'll discuss all the clinical application, and all these questions will be answered there. So you will not be able to understand this question right now or answer this question. If I answer this question right now, you will not be able to understand. So first, let me finish my cell survival curve, and when I will discuss the clinical application of linear quadratic model, which will start after, from third modules onward. I think all my modules have covered these questions which, which this participant has asked.
Yes. So there is one question like, how will we determine the D10 during the shoulder region, like the initial part of the cell survival curve?
How we will determine the
D10 in the shoulder region.
In the shoulder region. So let me tell you, experimentally, I will not be able to tell you. Only thing is that what I am trying to show you on the shape of the cell survival curve is that D10 ideally should reduce the survival fraction to 10%, while D10 is not reducing survival fraction to 10%. It will killing less than 90% of the cells, right? So they, as I told you in the beginning that I am not a radiation biologist, I have not really done these experiments, so I can't tell you, but of course, these values or these things have been very well generated in laboratory during experiments on cell culture and also on animal experiments.
If there are any further questions, you can put it in the chat box so that we can.
So all right, Dr. Deepa, if there is no more questions, so we can I think finish today's session, and I would like to thank all the participants, and I will again suggest that kindly be online by 5:30 tomorrow, because we will start at sharp 5:30. And as I told in the beginning that if you miss any concept, probably you will not be able to understand the subsequent part of it. So be ready tomorrow at 5:30. Thank you very much once again. Over to Dr. Deepa.
So before we end the session, there is one announcement that there is a Google form that has been shared. Link has been shared in the chat box. You please fill the form today, and once you complete, tomorrow there will be another Google form. So at the end of the session, 4-day session, we can issue a e-certificate. So for today, please share, fill and send the Google form.
So all the participants will be issued e-certificate at the end of
e-certificate, 4 days.
Right. Okay, so thank you very much. I am stopping sharing it. So, okay, bye-bye. See you then tomorrow at 5:30.
Dr. Manoj, have you left? Manoj? Has he left?
Yes, sir. I think Dr. Manoj has left. Just a minute. Dr. Deepa Joseph is there.
Sir has already left.
Oh, is that okay? Yeah. Good. It was a very good lecture, Deepa. You convey that to him.
Yeah, sure.
Yeah, it was an excellent lecture.